This is lesson 6.11, so improper integrals. And this is a BC topic only, so we're going to talk about what that means and how to evaluate those. So an improper integral has to do with where one of the limits of integration is infinity, or there's an infinite discontinuity in the interval somewhere, okay? So previously, we've just always, you got a definite integral and you were integrating from A to B, and previously to starting this section, you could always do that. But now we're going to learn that sometimes you're going to have to verify always that there's not a discontinuity inside the interval, either on an endpoint or in between A and B. And then it'll be really obvious that it's improper if there's an infinite symbol as A or B is one of the infinities, okay? So to be bounded, or a proper integral, means that from A to B is defined and it's bounded, the limits of integration are not infinite, and there are only finite many discontinuities in the interval, meaning there's just like a point that's missing or something. So improper integral, we're going to have two different cases. One of them is that either one or both of the limits of integration is an infinity, or somewhere in the interval from A to B you have an infinite discontinuity. In other words, we have an asymptote somewhere, either on an endpoint or within the middle of the interval. Okay, so we're going to see how to do this. Okay, so here's an example of the idea about why we do what we're going to do to answer this question. Okay, so we're going to look at integrating. We're going to look at what happens if we're going to integrate from 1 to some place t of 1 over x squared dx. So drawing 1 over x squared, we should know that that looks like this from 0 to infinity. There's another piece of it. If I were to draw it, there would be this part over here, but we're not doing that, so we don't need that part. So here we're going from 1 to t. So we're just going to say, okay, here's 1, and then somewhere over here, wherever, is t. And we're going to integrate from 1 to t, which means we want that area from 1 to t underneath this curve. So in order to do this integral, we would of course think of this as the integral of 1 to t of x to the negative 2 dx. If we integrate that, we're going to add 1, which will give me x to the negative 1, and then divide by negative 1. And we're going to do that from 1 to t. So if we plug this in, we're going to get minus 1 over t, because we'll have t to the negative 1, minus a negative 1, so we're going to get plus 1. So the thing that we need to figure out is if t, so if we let t go to infinity. So I just arbitrarily put t right here, but t could be way down, somewhere way along the line. And the idea is, what if I just said t goes all the way to infinity? So I want the area underneath, but there's actually no end to it. Well, what that would mean is I'm going to let t go to infinity right here. Well, if t goes to infinity, you'll have 1 over infinity, and that would be 0, and so we're going to get 1. Okay, so what that tells me is a of t is going to equal 1. That's if I'm going to infinity. Okay, so it's telling me that it's a of t, so a of t, if t is not infinity, is close to 1, right, for large values of t, and so that's the idea. So if we actually were to solve this problem, the way we would do it is we would say that we want the limit as t goes to infinity. Well, for this problem, that would mean the limit as t goes to infinity of a of t, which I just found a formula for, which was negative 1 over t plus 1, If I let t go to infinity, then this thing goes to 0, so my answer is 1. That means that the area underneath the curve from 1 to infinity of 1 over x squared is in fact exactly equal to 1. So this is one of those moments where you go, what? Because we're going to infinity, but we're actually able to find the area. Now, we're not always able to find the area, okay? But when we can, we would say that the improper interval converges. So this particular answer, this integral that we found, converges because the limit existed. The limit was 1. If it had not existed, so when we found the limit, we let t go to infinity, if we had ended up getting an infinity of some kind, we would say the integral diverges. Okay? If you have two different integrals, and you'll see an example of that in a minute, that would be like this case here, they both have to converge in order for the integral to converge. So if one of those was infinity, it wouldn't even matter what the other one did. It would be infinity. So easiest way to figure it out is honestly just to watch examples and see what you're doing, okay? To just follow the steps, okay? So here's what we do. So we're going to, very first thing is we're going to notice that this is improper because I have infinity. So the first thing I have to do is get rid of that. So I'm going to, and I just use the letters, it's A to B, it's in the top. So I'm going to let B go to infinity, and I'm going to replace the infinity with a B. Okay, so where I have an infinity, I can't really plug in infinity, so I'm going to have to plug in B when I do this integral, and then I'm going to take the limit, okay? So I'm just substituting that B in there. Now, I can't take the limit until I'm way at the end. So you're going to keep writing the limit as b goes to infinity. I can't do that till I've found the antiderivative, plugged in b, simplified, and so on. Then I can plug in and do the actual limit. So here we're going to recognize, okay, I'm integrating 1 over x. So we know that that's ln of the absolute value of x. And we're going to evaluate that from 1 to b. So still can't take the limit because I haven't even plugged in the b yet. So I'm still writing limit as b goes to infinity. Now I'm going to just do the fundamental theorem of calculus. I'm going to have ln of the absolute value of b minus ln of 1. Of course, I don't need absolute value signs for ln of 1 because 1 is already positive. Then I'm going to simplify that. Before I take the limit, I'm going to do one more step. And that is that I have ln of absolute value of b, and then ln of 1, of course, we know is 0. Well, now that I've simplified everything, now I can actually take the limit, which means that I basically plug in infinity. So I have ln of infinity. Well, ln of infinity, so we think about the natural log function. Remember, this is why you need to know what they look like. So here's the natural log function. So it is going to keep increasing as I go to infinity, so this answer is infinity. Well, what that means is, therefore, the integral from 1 to infinity of 1 over x dx diverges. That's what we found. So sometimes your question will simply be, does it converge or diverge? So here's that answer. It diverges. Okay? So that's how we handle it. So we're going to do the same thing. We're going to have to do a lot of limits here. Okay? Now, specifically, this is called a p-series integral. So in a very special case, if you are integrating from 1 to infinity of 1 over x raised to a power, it's going to converge as long as p, the power, is greater than 1, and diverge when p is less than or equal to 1. So let's look at the two examples that we've just done. This very first example, we looked at the integral. So essentially what we were doing by this third part here was we were finding the limit. This is essentially the integral 1 to infinity of 1 over x squared dx. That's what we actually found right here by doing that limit. Well, we found that it converged because we got an answer. Our answer was 1. This equals 1, and that works. Well, if we look at our formula, it says that it will converge if p is greater than 1, and 2 is definitely greater than 1. Now, if we go back to the example we just did, this is also a p series. Your power, you have 1 over x to the first, right? So p is 1, and we got an answer of diverges. Well, if we look here, it says it's going to diverge if p is less than or equal to 1, okay? So we're going to do a few examples, and then we're going to kind of look at a little bit about how we can kind of remember that or figure out what's going on. And I'll give you a basic synopsis here, okay? So basically, the reason that this one converges and 1 over x did not. So 1 over x looks very similar. The difference with 1 over x is that it does have similar shape, but it approaches 0, it gets close to 0 very slowly. 1 over x squared approaches 0 very fast. So it's because it goes to 0 and starts to approach 0 really fast that it will converge. Okay, we're not going to get into proving it and some of that stuff, and it'll make more sense later, but for me, sometimes that's very helpful to kind of understand, do I think something's going to converge or not converge on an integral? If I know that the graph is poking its way down here really slow, it's probably not going to converge. If it's coming down here and screaming its way close to 0, it's more likely to converge. So sometimes that just helps if you have the graph to kind of give you a visual. Okay, so let's look at example 3. So minus infinity to 0 of x e to the x dx. So again, new problem. I now have one of my limits of integration is infinite. Okay, so this is now a problem that I have an infinite discontinuity. So this is an improper integral. So I want to solve the limit as, now I like to use a, as a goes to minus infinity, and I'll put a to 0, x e to the x dx. Again, the reason I use a, it doesn't matter, you can use whatever letter you want. I just always use a for the bottom limit when I'm replacing it and b for the top. It just makes it easier for me to kind of keep things together. Okay, so then the next process is simply to keep writing the limit down until I finish doing that definite integral as far as I can go. Well, when I look at this definite integral, you should recognize right away that that's going to be something I'm going to have to do integration by parts. So what I prefer to do is go over here to the side and do the indefinite integral part. So I'm going to go over here and do this. I'm going to do that part, and then I'm going to come back in to the other side and write it in. So this is going to require integration by parts. So I'm going to have a u, and I'm going to have a dv that I'm going to substitute. So I'm going to let u equal x, dv equals e to the x dx. So that means v is also e to the x, and du equals dx. That's kind of crammed in there small, but you can, it should be pretty easy to do integration by parts now. So now my formula is u dv minus the integral of v du. Okay, that's how we do integration by parts once we've set it up. So now I can finish x e to the x minus, and of course the integral of e to the x is just e to the x, and then you would have plus c. So what I'm going to do when I come back over here, though, is because it's a definite integral, I don't write plus c. I just keep copying down my limit until I've substituted stuff in. But I'm going to immediately know, because my scratch work gave me the answer, that antiderivative is x e to the x minus e to the x, and I'm evaluating it from a to 0. So again, still can't do the limit because I don't have an a in the problem yet. So I'm going to write that down, and then I'm going to plug in. So I'm going to plug in 0 first. So that's going to give me 0 minus e to the 0 minus parentheses a e to the a minus e to the a. So in place of x, you're going to plug in a. Now I can do the limit, okay, because now I've got a's in my problem. So when I try to do this limit here, I need to figure out what is going on. So this, of course, is 0. E to the 0 is 1, so that's going to become a 1. And then I have to do, I'm going to plug in minus infinity. Oh, and interesting, we actually don't know the answer to this yet because we haven't done indeterminate forms for L'Hopital's rule. So I'm just going to tell you the answer for this one because that doesn't really work right. Here's how I'm going to do it. So 0 minus 1 minus parentheses. So this, if you put minus infinity in for that, that's actually an indeterminate form. So you would have to figure that out. And it actually ends up being 0, but we shouldn't know that actually from because we haven't covered that yet. So sorry, didn't know this problem was there, but my answer ends up being -1. All right, and so it does converge, okay? So I just want to make sure that you understand this is not 0 because e to the minus infinity is 0, because I have a minus infinity times 0, and we actually have to determine that, okay? So we'll just let that go on this example. It's because we're switching the order again of doing some stuff, so we'll have to cover that later. All right, so let's look at example 4. So example 4 gives me a different situation. This time I've got infinities on both. So I have minus infinity on the bottom and plus infinity on the top. So here's how we handle that. You are going to split this anywhere. So you can do minus infinity to 0, you can do minus infinity to 1,000,000, you can do minus infinity to -5, whatever you want. Well, I'm going to split it at the easy thing to plug in, which is 0. And so basically you're going to end up with 2 different integrals because I have to do the limits and the limits are different. Okay? So if you have both limits of integration are infinities, then you got to split it somewhere, anywhere in the middle that you want. And so in this case, again, 0 is easy to plug in, so I'm going to pick 0. Then each one of these will have its own limit. So this will be the limit as a approaches minus infinity, integral a to 0, 1 over 1 plus x squared dx, plus this one will be the limit as b approaches infinity, 0 to b, 1 over 1 plus x squared dx. So again, I'm replacing the infinities with a letter, and then I'm going to take the limit as it goes to infinity or minus infinity. You do not have to use a and b. You can use whatever you want. I just, again, lower limit of integration we usually call a, upper b, so that just makes it easier for me. Okay, so I can't take this limit yet until I'm done with some things, so I just always write that really fast. Then I need to do the antiderivative. Well, I hope we recognize 1 over 1 plus x squared as being arctangent or tangent inverse. So it's exactly arctangent of x, and we're going to evaluate it from a to 0. Plus, again, write the limit down because I can't do anything yet. 1 over 1 plus x squared, again, is arctangent or tangent inverse, whichever way you want to write it. Arctangent of x going from 0 to b. So now I'm going to take, again, I can't do the limit yet because I haven't substituted anything. So I'm going to have arctan of 0 minus arctan of a. That's the first limit. And then the second limit, b is going to infinity. And you're going to have arctan of b minus arctan of 0. Okay, don't forget you can pause anytime on a video. That's the nice thing about having notes this way. Now I have to figure out, okay, so what's going on here? Well, arctangent of 0. The question is, when does tangent equal 0? Well, tangent equals 0 at 0. So sometimes what we do is we'll just kind of write this. That thing goes to 0, okay? And then we'll do the same thing when we're kind of looking at the limit. What does the limit do? So arctangent of A, and A is going to minus infinity. So remember, this is the inverse of tangent. So we're saying, what is the angle value, or the radian, when tangent is going to minus infinity? Well, that value would be, so I'm going to write this down, 0 minus, that's 0 is this 0, 0 minus arctangent of minus infinity. So tangent goes to minus infinity at negative pi over 2. Again, the reason that knowing your graphs is really, really important, okay? Because we remember that tangent goes from negative pi over 2 to pi over 2. We have asymptotes there, and it looks like this. So as the angle we are going to, as we go to minus infinity, is negative pi over 2, plus, we're going to do the same thing here. So arctangent of B, well, B is going to infinity. Well, what is tangent doing? Where do I go towards infinity? That's at pi over 2. And then minus, again, arctangent of 0, which is 0. So we end up with pi over 2 plus pi over 2, which is pi. Okay, so if there's double limits of integration, both infinities, we just have to split it, okay, into 2. And then it's like 2 problems. Okay. If we look at example 5, and we were to look at the graph of this function from 0 to 5, okay, you would find that at 2, you would have a vertical asymptote, okay, and it's going to look like this, okay, and you have a vertical asymptote. So that means that at 2, it is not defined, okay? So starting today and forever, when you see an integral and somebody says, find this integral, the first thing you're going to have to do, if you see infinities for the interval ends, like the a to b, that'll be obvious. You'll be like, that's an improper integral. But the thing that will now be possible is that there's a discontinuity either in the interval or on the endpoint. And so you cannot just do the problem without considering that, okay? So this is considered improper. Yes, it is considered improper because there is an infinite discontinuity. In other words, a vertical asymptote here. There's an infinite discontinuity at x equals 2. So remember how we've talked about domain a lot, right? So you got a denominator. So as soon as you realize, hey, if I plug in 2, it's not defined there. So now I have an improper integral. It doesn't look improper, but it is, okay? So I'm not going to do the way B is written here, so we're going to kind of skip that. I'm just going to actually do the way you would do the problem. Okay, so I'm actually not going to write this either. So the way I would do the problem is I would simply recognize, if it'll catch up with me, okay. Okay. So what I'm going to do is I'm going to just say, okay, if this is me, I get this problem, somebody says, find this integral. From now on, the very first thing you should always look at for every single definite integral is it defined everywhere? It is not. It is not defined at 2. So that means 2 has to go away. So just a second, and we'll figure out what A needs to approach here. So we're going to take the 2 out, and we're going to put A in there. And I'm going to go ahead and rewrite this as x minus 2 to the negative 1/2, because I know I'll need it that way. So what is A going to approach? Well, A is not going to approach minus infinity, because that's not what it says. But A can't just approach positive, just 2 in general. It's going to approach 2 from the right. because I'm in the interval from 2 to 5, which means I'm on the right side of 2. So we're going to do the same process, but instead of infinity, I'm approaching 2 because 2 is where the problem is, okay? So again, you just have to keep writing limit, okay, for a while. Now let's do this problem. Well, you could use u substitution, but remember, if you are to let u equal x minus 2, du is just going to equal dx. So there's no reason for me to actually physically write any kind of u substitution. I'm just going to take this and raise the power by 1. So that's going to be 1/2. And then instead of dividing by 1/2, I multiply by 2. So that's my antiderivative. And I'm evaluating it from a to 5. Again, can't do the limit yet because I haven't substituted the a in there yet. So I'm simply going to get 2 times 3 to the 1/2, because 5 minus 2, minus 2 times a minus 2 to the 1/2. Okay, so I'm just simply plugging that in. So then I have to say, okay, so what is happening here if a approaches 2 from the right? Well, the first thing's a constant, so you're still going to have 2a, or 2 times 3 to the 1/2. That's a constant, so it doesn't have anything to do with a. On the second one, remember, you can just plug in a number as long as it comes out right. Well, if I plug in a, I'm going to, a is 2, so 2 minus 2 is 0. This is not a negative power, this is a positive power, so 0 is okay, so that's just going to become 0. So that means my answer is 2 square root of 3, or you can leave it 2, 3 to the 1/2. Okay, so again, we have an infinite discontinuity, we have a graph that has an asymptote, and I can still find the area underneath it. So, kind of a cool deal. All right, so kind of your definitions of being improper. So your possibilities for being improper is that you either have an infinity somewhere, or you have an infinite discontinuity at one of the ends. Okay, so like if C is the place you have a discontinuity, you're going to let C approach B from the right. If your discontinuity is on this side, C will approach that A from the right, or sorry, from the left. Here, this is from the left because A to B, you're on the left side of B. Here you're going from A to B, and A is the discontinuity, so it's on the side. And then sometimes your discontinuity is in the middle, and so you'll split it, and then you just have to deal with each of those integrals the way they work. Okay, so let's do this one. So here we have the integral from 0 to 1 of ln of x dx. Okay, so a couple of things. First thing, every time I'm going to look and see, do I have a domain issue with my limits of integration? Well, we already know that ln of 0, not allowed, right? We have our 3 domain things. We can't divide by 0, no negatives under square roots, and logs cannot have 0 or negative inside. So 0 is a problem here. So we're going to get rid of it then and say let a approach 0 from the right, because a to 1, I'm on the right side, ln of x dx. Now, you could do that antiderivative by doing integration by parts. We learned that, but that was one of those that I said, hey, you know what, if it were me, I would just memorize it. So the formula for integrating ln of x is x ln of x minus x. So again, either you have to do integration by parts to figure that out, or you have to do, you just memorize it. And if it were me, I just memorize it because it's a, you know, common enough one. All right, so again, still can't do the limit because I have to get my a in there. So I'm going to have 1 times ln of 1 minus 1 minus parentheses a ln of a minus a. Everywhere you see an x, you substitute an a. So here we have 1 times ln of 1. Well, ln of 1 is 0, so that's 0 minus 1 minus. Now here's another one, and I just realized that, darn it. So we can't actually do this limit either without some other steps. So we'll have to redo some of this when we've done the indeterminate forms for L'Hopital's to be able to do that, but you're going to end up with 0 and then minus 0 because you substitute for A, so we get -1. So we'll have to work on those indeterminate forms and all the methods to solve those to be able to do that. So I'll have to check over your homework. All right, so let's do one last example. And again, very first thing that I do is I say, okay, I'm doing an integral, it's definite, I have domain issues here because I can't divide by 0. So this thing is undefined at 1, which means what you're going to have to do is you'll have to integrate from 0 to 1 of dx over x minus 1 plus the integral from 1 to 3 of dx over x minus 1. So if the discontinuity is inside the interval, then you have to split at that place. Now it's like the last problem. So here I'm going to take the limit as b approaches 1 from the left because I'm going from 0 to 1. So now it'll be 0 to b of dx over x minus 1 plus the limit as a approaches 1 from the right, because I'm 1 to 3, so that's the right side of a of that same integral. So I'll just have these two limits to do, but luckily the antiderivatives are the same, so if it was difficult to do the antiderivative, I only have to do that once, but this one is easy. It's just going to be ln of absolute value of x minus 1. And we're going from 0 to b. Again, you just have to write the limit down because I can't do it yet. And I get the same thing, ln of absolute value of x minus 1. But this one goes from a to 3. So again, still can't do the limit because I have to substitute. So I'm going to have ln of absolute value of b minus 1 minus ln of absolute value of 0 minus 1. Here's the perfect example of why absolute value makes a difference. Plus the limit as a approaches 1 from the right of ln of 3 minus 1, which is 2, minus ln of absolute value of a minus 1. Okay, so now we're going to approach from the right of b. So that means this number, you can plug in a 1. You can't really plug in a 1 because if you plug in 1, you would have ln of 0, and ln of 0 is not allowed. So if you approach 0 from the right, because it's 1 minus 1, but I'm coming from the left. I'm approaching from the left. I'm going to get minus infinity for that part. And then this is ln of 1, which is 0. So this integral diverges. So it doesn't actually matter what happens on the right because this one diverged. So it's plus whatever irrelevant, it diverges, okay? Because this limit, the first one, was an infinite limit, then it doesn't matter what happens on the right, okay? Because if they have to both converge for the integral to converge. Okay, so since one diverges, we're done. Okay, so in class, next time, we will do some of those indeterminate forms for these limits so that hopefully you'll be able to finish your homework. But that's it for indefinite integrals, or improper integrals.